Good morning, good afternoon, everyone. I will start the seminar. Welcome, everyone, to the webinar on the value of water in Canada. My name is Roy Brouwer. I'm an executive director at the Water Institute here in Waterloo, the University of Waterloo. It's my pleasure to see you online. Welcome to the new term, the new series of webinars for the rest of this year. Our program for the winter term, January till April, is online as well. I can share the link with you. It's the same website as where you registered for this webinar. We're excited with the extension of the program into 2024. Before I introduce the presenter of today, I just want to acknowledge that I participate here from land that belongs to the traditional territory of the Neutral Anishinaabe and Haudenosaunee peoples. Our main campus of the University of Waterloo is situated on Haldimand Tract, the land that was granted to the Six Nations, that includes 6 miles on each side of the Grand River that you see here. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within our Indigenous Initiatives Office. Before I introduce the speaker also for today, please use the Q&A box if you have any questions for the speaker. Use the chat box only if you have any technical issues, and the producer behind the webinar series, Julie Grand, will help you with your technical challenges. Any questions, just use the Q&A box. You can use the Q&A box during the presentation, and we'll get to your questions at the end of the presentation. So without further ado, I'm very pleased to introduce my highly esteemed colleague here at the University of Waterloo, Professor Dr. Margaret Insley. She completed her bachelor's degree in economics at the University of Calgary, her master's degree at the University of Alberta, and her PhD at the University of Guelph, where her thesis research examined making optimal decisions under uncertainty in the context of the protection of groundwater resources. She's been at the University of Waterloo for over 20 years. She came here in 2002. She accepted a position here, teaching courses on natural resource economics and decision-making under uncertainty, and just recently, unfortunately for us, retired on August 31st. Dr. Insley's research explores how market uncertainty affects the efficient use of natural resources such as oil, timber, and water, and how negative environmental consequences can be reduced. She uses an approach called real options analysis, which makes use of the tools of finance to analyze decisions under uncertainty. And that's also going to be, to some extent, the content of her presentation today. So I'm very happy to hand over the floor to you, Margaret. Thank you very much for joining us here today.
Thank you, Roy. Thanks for the invitation to give a talk in this webinar series. I will now share my screen. So I hope you can see my first slide there.
Yes.
Good, thank you. I'll just my spotlight tool there. All right, so today I'm going to talk about protecting water quality using environmental bonds, and I'll be talking, I guess, more broadly as well about environmental bonds in general and how they can improve outcomes for the environment. So my particular specialty has been dealing with resource extraction industries, and as I think we're all aware, natural resource extraction has negative consequences for the environment. When we're talking about mining, which I'll talk about a lot today, we see drilling, digging, excavation, waste generation that can harm surface and groundwater quality during the production phase of a mine. And then after the mine closes, we see damages continuing to occur if remediation and cleanup have been inadequate. So again, talking about mining is water, rather, is the primary vehicle for transporting mine-related contaminants to the environment. And these water quality issues in mining are caused by acid rock drainage, the physical transport of sediment into water, and chemicals used in the extraction process. And then in addition, there's the creation of mine tailings, which are the wastes left behind after valuable metals and minerals have been extracted. These tailings contain toxic substances, and they're often contained in stored behind large dams that can reach hundreds of meters high, called tailings ponds. So abandoned and orphan mine sites are a big problem in Canada and the US and elsewhere as well. I'm going to use the terms abandoned or orphan mined to refer to mine sites where the owner has ceased or indefinitely suspended advanced exploration, mining, or production without rehabilitation. So I'm just clarifying that because sometimes these terms are used, are defined differently. So I'm using them interchangeably. So there are hundreds of thousands abandoned mines in the US. That's an estimate. The inventory is really highly uncertain, and the order of magnitude in Canada is tens of thousands. Some of those old mines have been abandoned prior to there being any regulations requiring cleanup. So the US federal government only brought in regulations in the 1970s to actually require reclamation of a mine site. And in Canada, the timing varied across different provinces, the 1960s in BC and Alberta, and quite a bit later in Ontario. So we see some mines some mines abandoned because they didn't fall under these regulations. But more recently, we see mines abandoned in spite of these regulations due to bankruptcy of the firm, of the owner of the mine. And we also observe bankruptcy being used strategically by firms in some cases. So a recent example of this is in coal mining in the US, where production and employment have declined significantly over the last decade. And we've seen a substantial increase in the bankruptcy of coal mining companies. And in some cases, this is to avoid costly reclamation bills. So firms go bankrupt, and then governments are left to do the cleanup. Further, we've seen some publicly traded large coal companies, which had no intention of going bankrupt, transferring old idle coal mines to smaller, financially weaker companies who are willing to exercise that option of going bankrupt. So we've also seen that transfer of these old mines to weaker companies, which then produce them for a while and then maybe take that option to go bankrupt. In Canada, we have also a problem with bankruptcy in mines. And here's an example. Canada's Northern Abandoned Mine Reclamation Program manages the 8 largest and most high-risk abandoned mines in the Yukon and the Northwest Territories, and these were abandoned when their owners became insolvent. These mines typically have high cleanup costs because they are very large. The Faro mine is often cited as an example, a bad example. It was an open pit lead zinc mine, one of the largest in the world, located in south central Yukon near the town of Faro. Millions of tons of tailings and waste rock were left behind, and that is leaching metals and acid into land and water. The mine owner declared bankruptcy in 1998, and federal government is funding the cleanup at an estimated cost of $500 million. And then I'll just mention this last example about mining, which you may have heard of if you were paying attention to the news in 2014. Mount Polley is an open pit copper gold mine in BC, and they had a very large tailings pond which breached in 2014. And this photo shows that breach with tailings flowing down the creek and into Quesnel Lake. And the conclusion was that the tailings pond had been operating beyond its capacity, so was not being managed well. Now, this is not an example of a bankruptcy. This this mine was closed for a period, but has since reopened. So now, going from mining to talk a bit about the oil and gas industry, we know there are negative impacts on air, water, and soil from oil and gas wells during production. But orphaned oil and gas wells are also a major problem, which we've heard a lot about in the news of late in the last decade or so. If wells are improperly plugged, they may contaminate water supplies, degrade ecosystems, and emit methane and other air pollutants. In the US, the EPA, the Environmental Protection Agency, estimates that as of 2018, about 2.1 million wells were not being used for production, injection, or other purposes, but had not been plugged. And it's thought there are many more that haven't been accounted for in inventories. These orphan wells are also a problem in Alberta, and the number of orphan wells increased hugely during the downturn in oil prices in the 2014 to 2016 period. In Alberta, only a small fraction of lands used for oil and gas extraction have been remediated. One recent estimate from 2021 was that there were 300,000 unreclaimed wells that would cost from 40 to 70 billion to clean up. And a significant number of firms have declared bankruptcy or also transferred ownership to weaker firms has also been observed in Alberta, as I was mentioning in relation to coal mining in the US. So what are the regulatory incentives that would induce a firm to clean up their waste after a well or a mine is closed? Well, one is strict liability. So most jurisdictions impose strict liability, which is an obligation to pay for site remediation at project termination or face court action. Strict liability laws can have a couple of unintended consequences. Unintended consequence number one is it gives it an incentive to remain inactive or mothballed in order to escape cleanup costs. So a firm doesn't declare a well or a mine closed so that they have to clean it up. They just kind of keep it in a mothballed state to avoid or delay those costs. And a study by Lucia Mullenbach from 2015, she did an empirical study of oil and gas wells in Alberta and found that a significant portion of those that were temporarily closed were actually likely never to reopen, even under ideal market conditions. The average length of inactivity for temporarily closed wells was 8.39 years in this 93 to 2007 period, but there was a huge range. That's just the average. Unintended consequence number two is that legal liability may provide an incentive to declare bankruptcy, because that's a way of avoiding those costs that you know you're liable for. And as an aside, this question has been dealt with in legal cases of late. Who pays for cleanup in the event of firm bankruptcy? And there was a case which was considered quite significant in Canada, the insolvency of Redwater Energy in 2015. And in a Supreme Court ruling in 2019, it was the Supreme Court ruled that Redwater must fulfill its environmental obligations before paying back creditors, which overturned a previous Alberta Court of Appeal decision, which said that creditors actually had first dibs on, remaining assets of Redwater. So this was considered a win for the environment and quite significant in environmental law in Canada. So another incentive beyond legal liability, another regulatory incentive for waste cleanup are environmental insurance instruments, environmental financial assurance instruments. So there are many types of these, of financial assurance instruments. Sureties refer to instruments such as surety bonds, performance bonds, and letters of credit. And these are guarantees issued by a bonding company an insurance company, a bank, or other financial institution which agrees to hold itself liable for the act or failures of a third party. So basically, the bonding company or insurance company agrees to pay for cleanup if the firm reneges on its obligations. And of course, it does this for a fee, which is charged to the firm. Another type of financial assurance is just a cash deposit. So firms are just required to deposit cash with a third party or with the government, and that cash is held in deposit until the cleanup is judged to have been done satisfactorily. Trust funds, pledges of assets, there's many different types. All of these instruments reduce the incentive for a firm to declare bankruptcy in order to avoid its obligation. The types of assurance that are demanded of a firm are variable and are often based on some judgment made of the credit worthiness of that particular firm. However, what we've seen in practice, and which I think is evident from the orphan wells, orphan mine problem that we observe, is that financial sureties demanded in many jurisdictions is inadequate. So one example of financial assurance is in Ontario, where the Mine Act of 1990 specifies that financial assurance is required that's equal to the estimated cost of mine rehabilitation. There are numerous different forms of surety allowed, and on the Ontario government posts on their website a list of all the financial assurance instruments that have been received. And I looked just yesterday, and there were 186 projects listed. And you can see here's an approximate breakdown of the types of assurance that have been received from firms mining in Ontario. And the total in that spreadsheet of all the financial assurance was a pledge up to $2.6 billion. So in Alberta, Alberta also has a form of financial assurance. It's really a pooled insurance mechanism managed by the Orphan Well Association. The Orphan Well Association is a body that collects an orphan well levy from well operators based on each operator's share of total province-wide liabilities. Historically, so this is insurance that's there to provide cleanup funds if a firm goes bankrupt or doesn't clean up adequately. But historically, this fund has been very inadequately funded. There's some new programs have been introduced in January 22 to encourage well closure, to try to reduce the stock of orphan wells and to reduce the stock of wells that are just mothballed and not cleaned up at all. And so this involves an inventory reduction program, which gives annual industry closure spending targets, and firms are given a target that they're supposed to meet. And those firms can elect to provide a security deposit instead of meeting their closure target. So given that background, what are the key regulatory issues for extractive industries? So what I see is there's two sides, two key issues. One is dealing with environmental damages during production. So dealing with waste and pollution as the mine, as ore is produced or as oil and gas are produced, and also dealing with damages which may occur as waste is stored. And then the second issue is the timely cleanup, ensuring that there's a timely cleanup done by firms, and avoiding firms delaying cleanup for a long time, avoiding firms declaring bankruptcy to avoid cleanup, ensuring that the firms do the cleanup rather than passing it on to governments, governments having to pay for cleanup out of general tax revenues is generally not an efficient solution, and also violates this fairness notion that the polluter should be paying for cleanup. So my research, and I'm going to present some results today from a paper that I wrote with Sarah Agakazam-Shurboff, who was a PhD student in the Department of Economics at the University of Waterloo. And the goal in this paper is to analyze the impact of an environmental bond in the form of a cash deposit. And we use a cash deposit because that's really one of the easier forms to consider, and certainly is used in practice. So we want to look at what is the impact of a cash deposit bond on firm behavior and also on the value of the resource extraction project. We want to compare a firm's actions with and without the bond, and we focus on the government cleanup operations. So in this case, we're ignoring the environmental damages caused during the production period. We're looking at rather incentives to make sure the waste is cleaned up. So that's the focus of this paper and this talk, the results I'll be presenting here today. So the case, in this case, the cases we'll examine and the results I'll present to you. For these results, we assume the firm is legally obligated to pay for cleanup costs at project termination. So that's a given. But we look at case one, which we're referring to as a benchmark, where the firm deposits a cash bond with the government equal to the cleanup costs. The bond is updated throughout the life of the project. So as more waste is created, the firm is required to deposit more into the bond. And also, if waste is reduced, so if the firm does some remediation during production, they will get some refund on the bond. So the bond is updated through the life of the project. The firm must remediate the site at the project end. And then case two is no bond is required. And we also consider two different models of bankruptcy, which I'll describe later. So here's a brief review. So we create, oh, I missed this slide. I thought I was getting ahead of myself here. So our basic approach then is to develop a stylized mathematical model of a firm's operating decisions with and without a bond. And we do this for a hypothetical copper mine. We're using a stochastic dynamic optimal control model. And this model, we think, captures the key features of the decision problem: mine opening, operations, mine closure, waste creation, and we model uncertain copper prices. We implement a numerical procedure to solve for the firm's optimal decisions or optimal controls, and also to solve for the mine value. How does the bond affect mine value? And then we use the optimal controls, which we've solved for, to in a Monte Carlo analysis to describe the distribution, the average and the range of key variables of interest and how they behave over time. Okay, so now on to cases examined, which I talked about. So now here is just a schematic showing, describing this mathematical model. So we have a copper resource, and we assume there's a known copper reserve. The firm decides to develop the resource, and copper is mined and produced. The firm produces waste during the mining process and can also abate waste, so it can reduce this stock of waste that's being produced. And then the copper is sold into the market for copper and we have stochastic copper prices. The firm chooses when to develop the mine, what is the rate of production. The firm can shut down temporarily during production, so can go into a mothballed state. What is the rate of waste abatement, when to close, clean up, whether to go bankrupt. And I just note there's a lease end date, so we assume there's a lease to operate this mine, and so closure has to happen by that lease end date. So if the firm does go bankrupt, it avoids paying cleanup costs and the government pays for the cleanup. We assume the firm and the government are equally skilled at undertaking site cleanup, and the cost is the same for a given waste stock. So they're equally able to do that cleanup. So this schematic shows the cash flows then. So we have in the upper half the cash flows to the firm, in the lower half the cash flows to the government. We see the pre-construction stage. The firm has to make a decision to spend the money needed to open the mine, to construct the mine. And when it does that, it makes an initial payment into this bond, this cash deposit, which it's required to do. And the size of this initial payment depends on how big that initial land disturbance is. So, so it makes an initial payment right off the start to get things going before the mine can start. The mine starts operating. During mine operation, the firm makes payments to the bond. The government pays interest on the bond. So this is just sitting in a deposit somewhere, and the firm will receive interest on that bond. Again, the firm can shut down temporarily and reopen if it chooses to at a small cost. And then when it decides to close, it pays the cleanup costs and it gets a bond refund. And the bond refund will exactly cover the cleanup costs because of the way the bond's designed. The bond at all times has to be adequate to cover cleanup costs. So this is the cash flows with the bond when the firm is not going bankrupt. So then just looking at cash flows if there's no bond, which is our other case, and here in this picture, the firm does go bankrupt. So we have the firm in the pre-construction stage again, undertakes construction to open the mine, can shut down temporarily if it so chooses. It will go, in this case, we're saying it goes bankrupt. There's no cost of going bankrupt. So now the government has to pay the cleanup costs in order to effect the permanent closure of the mine. So that's cash flows with no bond. And then just looking at this is the one equation which just shows the total cash flows for the firm. I just want to make a couple of points here. So pi denotes cash flows. Price times quantity of copper is the revenues from mining. This C is operating costs, which is just assumed a linear function of copper. This cost, C superscript A, refers to the abatement cost, which is a model as a convex abatement cost function, meaning that the more abatement, the more that waste the quantity of waste produced is reduced, or the quantity of waste is reduced, the higher is the cost to do so at the margin. So this is a convex cost. Then we have some fixed costs here, just a constant. And then here are the cash flows from the bond. So this minus dBdt shows the firm paying into the bond. So the bond grows, and this is a deduction from the firm's profits as they're producing. And then here's the interest that is paid on the bond, rho times B here. So the interest paid on the bond, we assume we denoted that as rho. And then let R denote the opportunity cost of capital for the firm. So the cost to the firm of raising capital, or what it could earn in the next best project that it could undertake. In this numerical example, we assume that the firm is getting interest at its opportunity cost. And this is an important assumption. In practice, it would often be the case. I mean, some bonds, for some, pay no interest at all, or in some jurisdictions, interest is paid, but at less than what the firm would consider their opportunity cost of capital. And we can clearly examine that assumption and look at the impact. But for this presentation, I'm just sticking with this: the firm is paid interest at its opportunity cost of capital. Then just a word about modeling bankruptcy. So, of course, many factors determine the decision to go bankrupt. What are the legal consequences? How big is the firm? Where are the firm's assets held? Does the firm intend to take future projects in the same jurisdiction? So, bankruptcy is a complex decision. Some contributing factors are beyond a firm's control, such as commodity prices, whereas others are controlled by the firm, such as the operating choices they make along the way. So we define two types of bankruptcy, exogenous and endogenous. In this presentation, I'm just going to talk about the endogenous type of bankruptcy. The endogenous bankruptcy is defined as follows. The firm is bankrupt if the value of the mine is negative. So as soon as it goes epsilon less than 0, then it's assumed the firm is bankrupt. So clearly this is affected by copper markets, the price of copper, but it's also affected by the firm's operating decisions. For example, how much to spend on undertaking waste abatement. The other type we look at in the paper is just assuming bankruptcy is just random. It's just a Poisson process, which is unaffected by the firm's actions. But I won't talk about that here today. So this, I think, reviews what I've said already. The firm makes some choices we call optimal controls. These are feedback controls. They choose production, rate of abatement, the stage of operation. So, the timing of starting construction, production, and so on, when to abandon, when to go bankrupt if you're going to go bankrupt. The project has to be terminated by the lease end date, capital T. So the actual termination date is the minimum of these TA, TB, and capital T. So the total project value is the sum of the value to the firm and the value to the government. So we're not just looking at the impact on the firm. We want to know what is the impact of this bond to the value of this mine to the government as well. So we're trying to look at really the total value of this mine to society, looking at the firm and the government. The value to the firm is just the sum of the present value of expected cash flows to the profit maximizing firm over the operating life of the mine. The value to the government is the sum of the expected cash flows to the government, which are essentially the cleanup costs. That's a negative if it has to pay cleanup costs. And also this is a negative amount. It's either the cleanup costs or a bond refund to the firm, either of those. So in the paper, we have a theoretical result, which I'll just summarize briefly before I show you the numerical results. This theoretical result, I think, is actually makes sense once you think about it, that under certain assumptions, when you have a certain type of bond, and it's the type of bond we use in this paper, if you have this environmental bond that holds to these assumptions, then the possibility of bankruptcy has no impact on the firm's decision. So then if you impose this type of bond for the firm, it's just like they're operating as if they're never going to go bankrupt. And so in a sense, this is a way we can say the firm is behaving optimally from society's point of view because the bankruptcy risk is not distorting their decisions. So the key assumptions for this to hold are the ones that we make for our case one. The government pays interest on the bond at the firm's opportunity cost of capital. At all moments in time, the bond fully covers cleanup costs, and bankruptcy occurs when the value of the project is less than or equal to 0. So this is our benchmark case one. And in this case, the firm really essentially operates as if it will never be bankrupt. All right, so our numerical example, we assume copper prices follow a stochastic process, as I mentioned. So here's a common model of copper prices, and this is the drift term here. So this is a differential equation describing copper prices. I guess this is equation number 2 in this paper. This shows what's happening to the level, the copper prices over time. This is a trend over time, and this is the uncertainty component, where dz is equal to theta root dt, where theta is a standard normal random variable. So this is an Ito process. And then kappa, mu, and sigma are constant parameters. And what you can see is with this term, this drags copper prices back to a long run mean, which is related to mu. So this is copper prices tend to be pulled back to a long run mean, which would be related to the supply and demand for copper in the market, but there's this volatility. So we estimate these parameters using a common filter on futures prices, and we make specific assumptions about cost functions and other needed parameters. We assume the project life is 15 years. This is a picture I thought would be interesting that shows what happened to copper prices from about 1996 up to 2016 here. And the red line is, the blue line is actual spot copper prices, and the red line are model implied copper prices in US dollars per pound. So our model of copper prices can track historical prices fairly well. And you can see how highly volatile copper prices are. All right, so now some numerical results. So here's a graph showing dollars, US millions of dollars on the vertical axis and the waste stock on the horizontal axis. So this waste stock is just giving the stock the size of the land disturbance that's created when the mine is open. So, you know, as this gets bigger, it means this, we're talking about a larger size mine. So what we see here, so we're just going to pay attention to the pink and the black line. So this is the case, this is sort of our benchmark case where there is a bond. And here's the pink line where there's no bond. And you can see the project value is higher for the firm when there's no bond. So this is the expected value of the project to the firm prior to construction. So if the firm were to sell the land, this would be the fair market price of the land where a mine can be constructed. So this, the value of the bond reduces the value of the project to the firm. And showing some numerical amounts here, we see the firm, and now we can add in value to the government. We see here's the firm value with the bond was 574 million, 650 million with no bond. So we see that difference. But then we see the government value isn't negative here, because when there's no bond, the government's going to end up having to clean up some of the waste or all of the waste. The firm will go bankrupt with some probability over time, but by the end date, it will with 100% probability go bankrupt rather than clean up the bond. And so the government has this cost it has to bear. So the total value of this project, firm and government value, is less than the total value when a bond is imposed. So why is this? You know, why isn't this just the costs are shifted from the firm to the government, but the total value stays the same? Why is that? Well, the reason is that when there's a case with no bond, the firm is acting non-optimally. And we'll see that in the next slide or two. Okay, so this slide shows critical prices to launch the project. So we are able to determine what is the minimum copper price that has to exist for the firm to be willing to start constructing the project. So the higher is the critical price, the less likely the firm is going to start that project. So we can see that when there's a bond here, this red dotted line, critical prices are higher. The project is less likely to be undertaken and then when there's no bond. So we would expect when there's no bond, there's going to be more copper mines undertaken. So this shows our Monte Carlo results where we can track what's happening over time. And what we see here, these are annual abatement rates. So this is the company's cleanup efforts. So as they go along, they can reduce some of their waste stock. And you can see when there is a bond, this black line, the firm is much more willing to reduce its waste. It abates at a greater rate than when there is no bond. This is pink line is the no bond case, and the other lines we ignore because that's the exogenous bankruptcy case. So the pink line, so we see that the firm with no bond, there's less waste abatement. And that is the cause of that difference we saw back here. Right? The reason the total value goes down is because the firm abates less waste, so leaves a larger amount to clean up, and that is reflected in the government cleanup costs and the total value of the project. So because there is no bond, the firm is, you know, behaving non-optimally from society's point of view. It's behaving optimally from the firm's point of view, but from the society's point of view, it's behaving non-optimally by generating too much waste. The probability of abandonment or bankruptcy is shown in this graph, and we look at these two lower lines here, and we can see with no bond, it's the firm is more likely to, in this case, declare bankruptcy. And by the end of the lease date in this model, there's 100% probability that the firm would declare bankruptcy. Because by doing that, it can avoid cleanup costs. And we're assuming in this model that there's no other costs of bankruptcy to the firm. So to summarize the key results, this mathematical model, which I think provides, although it's very simplified, of course, I think it provides some good intuition for the use of environmental bonds. So the ability to declare bankruptcy is valuable to the firm and affects the firm's operating behavior. With no bond, projects will be launched sooner or more projects will be undertaken, and the resource stock is produced faster and more waste is created. This implies an efficiency loss for society as a whole, although the firm is acting in its own best interests. An environmental bond can fully collateralize government and thereby avoid any deadweight loss from leaving cleanup to the government using general tax revenue. Not requiring a bond will increase the number of firms in the industry, but at the expense of government having to pick up a significant cleanup tab. And there's some interesting empirical work by Boomhauer in an American Economic Review paper from 2019, which did an empirical study in Texas where bonding requirements were made more strict some years ago, and they noted significant consolidation in the industry, that firms, smaller, weaker firms did leave the industry as a result. So I note we have not addressed the negative environmental consequences of the waste stock. A pollution charge dependent on the stock size could be included as part of the bond mechanism. So we haven't looked at that here. So that this work, the results I presented was done a couple of years ago. The work that we're currently doing is making this model more realistic and looking at the impact of a more realistic bond type for the firm and for the government cleanup liability. And we're looking at considering a surety bond where the firm makes a stream of payments to a financial guarantor and thinking about what fee should be charged by the guarantor to take on this risk. We're looking at what's the impact on the government's cleanup liability if the bond is less than the full amount. And we're also looking at the effect of taxes and royalties, which, we did not have taxes and royalties in there. And of course, mining and oil and gas both pay significant taxes and royalties, which will interact with the environmental bond and also need to be considered. So that's something we're also looking at. And we're looking at in the context of the oil and gas industry and oil well cleanup at the moment. And that's the end of my talk. Thank you so much for listening.
Thank you very much, Margaret. We have time for questions. If you have any questions, please use the Q&A box, and then we'll get to your questions. I don't see any questions at the moment. I can kick off the discussion and give you some time to think of a question that you would like to ask Margaret. So I think you already mentioned it a little bit in the assumptions in one of your last slides, because I was wondering about the bond being the only mechanism through which you internalize the externalities associated with the mining operation. So the assumption here is that cleanup is the most cost-effective way of addressing the pollution. There is no prevention, for example, that you perhaps would address with a pollution charge. I saw that you had that in your previous slide as well. But,
right. Yeah. So I think that's yes, I think we debated adding in a pollution charge as well, but then we wanted to just get at the bond itself. That's, I think a lot of literature has looked at pollution taxes and pollution charges. Which, yeah, I mean, you could imagine the pollution, the bond being, including a pollution charge in it, right? You can imagine a mechanism like that. But I guess typically in regulation, they are looked at pretty separately, right? The sort of cleanup issue is looked at quite separately from the pollution generated while operation takes place. So I guess our assumption is, that the waste. So one thing I didn't mention is in that model, there's a maximum size on the waste stock that's allowed, right? So you could, so that's sort of one, and it's kind of assuming that that's the optimal size of the waste stock, right? Which may well not be the case if you take account of damages while the waste stock is sitting there.
Yeah, so that actually answers my other question, because you showed that if you don't have a bond, that incentivizes firms to behave from a social welfare point of view, not in a non-optimal way. But I was wondering, is there no other regulation than a bond? But you just answered the question. You actually impose a restriction on the amount of waste.
Right. Yeah. So there's a maximum waste stock size. So that, so it's kind of you're managing, which I guess for a tailings pond is quite reasonable. As we saw with Mount Pole, it was operating beyond a maximum that caused that big disaster. So they're managing this size of this, and that affects their production rate, how much they can produce from the mine.
Yeah. We in the meantime, we have a question from Kathleen Cameron. She's asking you, does the bond prevent offsetting costs to the consumer when a per dollar amount insurance payment is done? That is 0.10 of every or 10 cents from every dollar goes towards the special portfolio with the specific purpose of cleaning up the project. I thought this was how the oil and gas in Alberta was supposed to take place.
Right. So so that's quite different in Alberta. So so the so you wouldn't need that fund as they have, and if you had a bond that covered cleanup costs completely. So this is considered quite a strict bond, right? That you have to fully cover your cleanup costs with a cash deposit. And so in Alberta, as you mentioned, they have this fund which acts as an insurance scheme really for all the firms, and firms pay a levy into it. So but there's, in terms of the incentives that it gives the firm for smaller, weaker firms who don't have a strong interest in, I guess, maintaining their reputation in the industry, that's kind of allows them to free ride on others, right? So others are paying this fee, and and it so that the larger firms, I guess, are subsidizing the weaker firms, and it's the weaker ones that smaller ones that tend to go bankrupt.
Yeah. So Kathleen also has a follow-up question. Do the bonds also apply with agriculturally based firms as with livestock lagoons?
I am not aware of that, but I am not aware. I think if they are, that's a good question. I think with agriculture, so with mines, there's a set life of a mine and a cleanup time by which the mine has to be cleaned up. With livestock, I think that's more of an ongoing operation. It's my understanding, but so I'm not aware of that. But I think in general, bonds have a very are very applicable in many industries and are really a good tool, I think. And I think as our model shows, that if it's a cash deposit, but if firms receive interest on that cash deposit, it's not so costly to the firm.
Yeah. Margaret, I was also wondering whether whether firms who then deposit the cash, even though they get this interest rate back that covers the opportunity cost of their capital that they put into the bond, wouldn't firms be inclined to also transmit on top of that, perhaps, to include the abatement costs or the cleanup costs in the price for the copper?
I guess, well, copper is pretty well, determined in world commodity markets. So I guess, right, firms don't have much control over the price of copper, at least in Canada, right? So I think our exogenous model of copper prices is quite reasonable. So but it's determined in worldwide markets, so we don't have to worry about whether firms are passing on the cost in the price of copper, for example.
Okay. That makes sense. And so Kathleen comes back. So she asks you to clarify, the bonds are best used where a project has a specific life end date involved.
Well, I guess, so I say, so in the model that I showed here with the copper mine, you can say the bond has to be, or the copper mine has to be cleaned up by this date, and then you have this deposit which ensures that it cleaned up. So I think maybe the type of bond that would be more appropriate to your question is a performance bond, and those are certainly applied and could be applied in agriculture, I think, right? So where you have to meet a certain performance level. So you're not paying for a certain cleanup, but that's happening at the end of the life, but you have to pay a bond. You have to pay into something which is there in case, in case your activities are not meeting certain standards and you have an accident or something like that, which shouldn't happen. So it's a type of performance bond. And that's an interesting and useful tool, which I honestly haven't looked at, but I think that's a good point. That would be applicable, I think, in an agricultural setting where the problem with that is that it's quite costly to monitor. So you need a lot of monitoring happening where, the inspectors have to go in and check about whether the performance standards are being made.
Thanks. Maybe one more question from my side. I think you hinted at this already a little bit, that the bonds basically cover all the cleanup costs. But and then in your simulation you took I think a 15 years time period. Given the fact that some of the environmental pollution or the environmental damage only manifests itself over longer periods of time, I was wondering a little bit whether such in that context, a relatively short period of time, 15 years, whether that was sufficient to be able to internalize all the externalities, all the environmental damage costs. Right.
Yeah. So that's an important issue, and some of, for some industries, and you don't know what's going to happen down the road, and actually monitoring has to happen for a very long time, right? So I think a bond, and I believe this is the case from my reading, that the cleanup costs can include a certain amount for future monitoring, right? So that's a cost that has to be there. It's a sticky question in terms of when is the firm finally off the hook, right? So their liability is gone. So in the oil industry, for example, there's certain standards for plugging wells, but those standards have been changed over time and become stricter, and the monitoring has become better. And so firms that close their well at one point are generally off the hook for damages that occur later. So that's, in terms of bond policy, that's something that needs to be thought of very carefully, is when is liability over, and what type of costs or what type of fund do you need to ensure that that's part of the cleanup actually is some money that is there for future monitoring.
Yeah. Perfect. Thanks very much. I don't see any more questions. We're very nicely on time. We're 5 minutes to the hour. If there are no more questions from the audience, I want to thank you once again very much, Margaret, for giving this fantastic presentation. It was very insightful. I hope you all enjoyed the presentation. Thank you all online for participating. I look forward to see you again in a month's time. We will have Melissa de Jong on the 11th of October. Talking about the way Pollution Probe, a Canadian charity, of which she's the Policy and Programs Director, how Pollution Probe addresses the value of water in their various projects. So I look forward to see you again online in a month's time. Thank you for participating. Thank you very much to Margaret one more time for giving this presentation, quite a unique one. I believe some of this work has also been picked up by the European Commission already. So thanks very much, Margaret, for sharing your work with us. Take care, everyone, and looking forward to see you again in a month's time. And thanks very much to Julie Grant, who produces this webinar series with me. Thank you so much.
Thanks. Bye.
Bye-bye.